Hi, let's continue with this MOT2 crystal and analyze the twinning. I'm in the same data set as before. I'm going to come back to the lattice wizard. I'm going to peak hunt again because if you've just run a complete data reduction, then you're going to get a different peak table than you had originally. So we'll get back the kind of raw peak table from the actual frames. And I'm going to go to eWorld Explorer again. I'm clicking these ABC buttons to get different views of the lattice. It's a little tough right at this moment to spot the reflections of the second component, and it's not always easy. I'm trying to turn this around, and maybe there's certain angles where I can see some X shapes. Honestly, often the computer is pretty good at finding the second twin component itself. So I'm going to click on the Activate Twin Multi-Crystal button and come down to Find Next Component in Wrong Peaks. Click that. It finds a second component. The indexing percentages are 65 for the first, 39 for the second component, which gives you a hint that it's probably onto something real. The twin operator is 180-degree rotation around a reciprocal axis. It's always going to be one or the other. It's going to be a reciprocal axis, which is the normal to a plane in direct space, or else sometimes it's an axis in direct space instead. We can come down to this table of matches by component. UB1 is the original lattice that we assigned. UB2 is the twin, or the second twin domain. Overlap is what it sounds like. It's reflections that belong to both of these components. And then we do have a few wrong reflections left over, but 87% indexing between the two components. That's pretty good. So if we got something like a 54-degree rotation around a random direction, or if the indexing of the second component was just a few percent, then that would be a sign that we should click on the component, clear it, and add the next component again, and see if it comes out right the next time. Oh, this is funny. We got a different setting of the twin law this time, where now the rotation axis is the 100 direct axis, and the reason for that, I'm sure, is the second component was found in a different orientation this time, but it's going to be the same component. So when we found our two twin components, we can close eWorld Explorer, close the lattice wizard, data reduction with options as before, and as long as we found two twin components, the twinning box on this first screen is going to be checked. It's going to know what you're trying to do, so normally you don't have to do anything with that. Clear data like before. The defaults are going to be different in this screen, but the defaults for twins, they do work well for twins, so it's probably safe to leave everything. We already decided to use average background. We know what the space group is now. We got a good solution in P21 upon M, so that means we can leave the outlier rejection on the default, which is monoclinic symmetry. The space group determination is on manual, and I'm going to change the output name. It's still May. This is our second data reduction, so I'm going to call it Dan2. I'm going to hit finish here. So this takes a little longer because it's going to go through the frames and look for each twin component individually. and then after that it's going to integrate them together. In these integration masks, you might be able to see the split peaks that we look for as a sign of twinning. Okay, now we're all set. Sometimes space group assignment is a little funny for twins because you're using only a subset of reflections here. It's only the non-overlapped reflections that get brought into the space group determination. It's normal to see your RInt values a little higher for twins, and that's basically the reason. We're using a subset of reflections. We already know the space group, so this is kind of ceremonial. With what I mentioned about a subset of reflections, you can see that some of these families of absences have no reflections in this data set. So it can be a challenge for space group determination because your absences just aren't detectable one way or the other. But anyway, we know that it's P21 upon M. And I'm going to type in z equals 4 here, which we determined before, and I'm going to hit finish. All right, let's look at a couple things right now. First, the twin HKLF5 statistics. That's a merged file that contains intensities from both of these components. We want to check that the RInt for the HKLF5 file is good. Right here we have 9.8% for the merged file. Again, relax your expectations a little bit when it's a twin because overlap and so on is going to make this tricky. But 10% and not 30% shows that everything went basically okay. We also want to check the decomposed statistics for each of the individual components. The main thing that I'm looking for here is one of these significantly stronger than the other? In this case, the example is yes. Component 1 has I over sigma 14 and RInt 10%, which is decent. The second one has I over sigma 7, which is much weaker, and RInt correspondingly is also a lot bigger. So that's a sign that the isolated reflections of component 2 are much weaker data, and it would probably be wise to just leave them out. So we'll do that in the twin data refinalization dialog. The twin finalization is right under the other one. There's a few more changes that we're going to need to make in here. First, check the chemical formula. For some reason, it keeps trying to give me a z of 2 here. So I'm going to change it back to 4 and set mu in formula. I'm going to check apply absorption correction, and we're going to use an analytical correction just like we set up before. You can check here that the absorption correction is set up correctly. We have a mu of 22, which is correct for, if you notice, this is right for z equals 4. Over here under scale 3 abs pack, we want to change this to separate scales for all components. That just works better. Under space group determination, we want to change this to interactive mode. The next thing is under HKL file. We decided that the second component is weaker, so that means we're going to use reflections from component 1 only. Under merging, we do need to merge data. This can normally stay on the default as long as you went through the integration with the right lattice type. So we protect ourselves here by doing a quick solution, ascertaining that the space group is P2 on M, and then going through the second data reduction with monoclinic symmetry assumed. So the only thing we need to do is turn on outlier rejection. The last thing is change the output base name, and we're going to follow the same convention as before. We started with Dan2, so now this is going to be Dan2 underscore core. Okay. We can say yes to this. It's going to give us the same space group determination as before. We can see that our RInt numbers got better probably because we applied an absorption correction, so that's nice to see. I'm going to pick P21 on M, and I'm going to change the Z again. Okay, we're all set. And we can see that by leaving out the second weaker component, the RINT statistic for our merged HKLF file went from 10% to 4%, a combination of leaving out the weaker reflections and applying an absorption correction. So now it's looking like we have really good quality data. I'm switching over to Cygwin. I'm already in the same directory that I have my full data set in. I'm gonna make a directory in here to make everything easier to find. I'm gonna call it work. I'm gonna switch into that directory, and I'm gonna make a directory for the individual integration that we just did, which is dan2_core. And I'm gonna copy the parent folder, anything starting with dan2_core, and copy it into dan2_core. Oh, I'm missing a star here. There. Now anything starting with those words. Okay. So the files we have here, it's a bit longer of a list when you're working with a twin. We have twin1 HKLF4.HKL and the corresponding twin1 HKLF4.ints. This is a file that Chrysalis attempted to separate the reflections of the two components and give us only the first component. And that's the file that's suitable for solving in shellxt. So I'm going to run shellxt dan2_core_twin1_HKLF4. Oh, I don't have, that's funny because I have shellxl on here. I'm going to pause this video for a minute and come back for part 2. Okay, we have shellxt working now, so we can keep going. I'm going to go ahead and solve the structure dan2_core twin1 HKLF4. We get a few candidate solutions here. We know that the one in P21 upon M is the correct one, and that's _A. So let's open that in OLX2. dan2_core_twin1 HKLF4_A.res. For now, we're just going to make sure that everything looks okay here, and I can tell by growing it out that this is the same structure as before. So yeah, everything is good. We're happy. Let's go ahead and prepare this file so that we can refine it against the full combined data of the two components, which is the HKLF5 file. You're going to notice if I list this directory, there is no HKLF5.ints file in here. And that's because we're intended to take the solution that we just got and copy it over and use that as the ints file for the HKLF5 file. So I'm going to copy dan2_core twin1 HKLF4_A.res, the shellxt output. I'm going to copy it over to the HKLF5 name, and I'm going to make this an ints file. And now I'll edit this file that we that we just created to make just a couple small changes. All right, maybe you can remember that when we do a twin refinement, we have to add a BASF instruction, which is the batch scale factor that measures the volumes of the two twin components. So I'm going to put BASF. I'm going to give it a starting value. 0.5 is fine. The only other thing I have to do is come down to the bottom where it says HKLF4, and I'm going to change this to HKLF5. So only two changes to make here pertaining to the twinning. There's BASF before the first atom, and there's HKLF5 at the end of the file. Let's save this and run a refinement. Okay. There's an unknown element H on the bond instruction. What that means is this structure has no hydrogen in it, but shellXT was trying to be helpful, and it gave us a bond $H instruction. So I'm just going to delete $H from the bond instruction, and now we should be able to refine. Okay, the refinement looks pretty happy. We have 7% isotropic refinement. That's pretty good. And as for the rest, I'm going to let you finish up this refinement and see exactly how the results compare before and after we handled the twinning. Okay, thanks for watching.